Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 3, 2026, just 2 days ago. It presents a method where large language models can retain nearly 100% of their original performance while storing only 256 tokens in their memory cache. The paper is titled FASA, Frequency-Aware Sparse Attention, and as we'll see later, the way it uses frequency patterns to pick those tokens is really quite clever and leads to significant speedups. Alright, Table 1 explicitly quantifies this benefit using compound contextual agreement scores. The columns represent different memory budgets, K, ranging from a tight 64 tokens up to 2048. The top rows list standard baselines like random and snap KV. Below the divider, we see the results for the proposed method using varying numbers of frequency chunks, labeled F. Crucially, look at the first column where the budget is only 64 tokens. With just 8 frequency chunks, the method scores 43.0, effectively outperforming the snap KV baseline of 37.9, which confirms that these dominant frequencies carry the most weight. So while Table 1 gave us the numbers, Figure 1 visualizes the mechanism, functional sparsity. We see heat maps for Metalama 3 on the left and Mistral 7b on the right, plotting attention heads against frequency chunks. Notice the distinct, dark vertical bands. These represent dominant chunks that capture context across almost all heads. Since the rest of the grid is pale, it confirms that most frequencies are redundant, which explains why pruning works so well. Well, Figure 2 maps out how the system actually uses that sparsity in a practical pipeline. On the far left, a one-time offline calibration step identifies which frequency chunks matter, producing a static map. Then, in the middle, the token importance predictor, or TIP, uses just those yellow dominant chunks to rapidly scan incoming data and select the most critical tokens, such as T1 and T7 here. Finally, on the right, the focused attention computation performs the heavy-duty full attention, but crucially, it only processes that small, selected subset, which is what drives the massive reduction in memory usage. Now, Table 2 translates that mechanism into raw performance on the Longbench V1 benchmark. The columns display scores across diverse tasks from single document QA to code generation. If we focus on the first model block for Llama 3.23b, the difference is stark. FASA achieves an average score of 41.5, effectively matching the Oracle upper bound. Meanwhile, baselines like Quest and Stream suffer massive drops, losing over 10 points of accuracy as indicated by the red arrows in the far right column. Okay, while the previous table covered general tasks, Table 3 specifically targets complex reasoning using the MAF 500 and NEIM 24 benchmarks. The top block details performance for the distilled Llama 8b model. If we look at the strict budget of 300 tokens, we see a dramatic failure in standard baselines. For instance, Snap K versus collapses to an accuracy of just 21.6%. FASA, however, holds strong at 62.2%, proving it can preserve the critical chain of thought that other methods simply discard. Moving to Figure 7, we see the trade-offs between memory and speed. This chart plots sequence length against memory usage on the left, shown by the bars, and inference time on the right, tracked by the lines. If you focus on the 64K mark, the green cross-hatched bar for FASAM shows a clear memory reduction compared to the blue baseline. But for speed, the red dashed line for FASAC is the standout. It remains nearly flat, avoiding the steep latency spike seen in the blue line, and achieving roughly a 2.56 times speedup. So wrapping up, FASA proves that we do not need the entire key value cache to keep large models smart. By leveraging the discovery of dominant frequency chunks, the method filters out noise to retain only the most critical tokens, offering a practical way to run massive contexts on standard hardware. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.